Welcome to Empowered Learning. This is the third video in the video series covering the topic of Taylor and Maclaurin polynomials. So in the first two videos, we introduced what the Taylor and Maclaurin polynomials are in their corresponding series. We also listed 6 questions that we had in terms of these special types of power series, in being able to unpack all the things that we need to know about them. And so in the first two videos, we covered the first 3 questions and we answered those. So in this video, we are going to answer the last 3 questions. And I have those 3 questions stated here again, just as a reminder for those of you that have been watching the video series. For those of you that are just running into this video and you don't know what the first 3 questions are, I would highly advise you to go look at the part 1 video if material on just the basics about Taylor and Maclaurin series is what you need. So our fourth question is there a list of well-known power series representations that we can reference? And so we're going to answer that question first. Next, if our power series representation of f of x actually equals f of x, how can this information be used to integrate functions using integrals that have non-elementary functions as antiderivatives? And the last question, can we multiply or divide well-known power series representations of functions in order to form other functions? Okay. So, of course, for that last question, the answer is yes, and we're actually going to use the product or quotient of functions that we already know in power series form to be able to represent integrands in power series form so that we can take the antiderivative of them in polynomial form, essentially. Okay. All right, so the first thing we are going to do is we will give the list of some very well-known functions, but we're going to give those functions in power series form. And then essentially questions 5 and 6 is, now that we have this list, how do we use it to do some of the basic things that we want to do in calculus? And of course, one of the main things that we want to do is be able to find out what is the antiderivative of a function. Okay. And so that's where we go to now. In answering question number 4, the list that follows shows some well-known Maclaurin series representations of functions that are often used. If you remember, a Maclaurin series is just a Taylor series where the number that we center the polynomial around is just going to be 0. The corresponding radius of convergence will be given for each of these power series representations as well. And so now we'll get into the list. So our first function is 1 divided by 1 minus x. And of course, we could represent that as just the sum of x raised to the n equals 0 to infinity. And of course, this is like our quintessential geometric series where our common ratio here is just x, okay? And our first term is 1. Of course, the radius of convergence for this one is 1. And since we're centering this particular Taylor series around 0, then of course, as long as we choose values in between -1 and 1, this particular power series will converge. And again, I'm calling it a power series because a Taylor series is essentially a power series, but we define our coefficients for the power series as just the nth derivative of our function evaluated at a divided by n factorial. So we see for e raised to the x, we have the summation of x raised to the n divided by n factorial. And we know that this particular Maclaurin series will converge for any x value. Same thing with sine and cosine. We've already seen the representation of sine of x in the second video in this video series. So we saw how, sine of x is essentially the summation of -1 raised to the n times x raised to the 2n plus 1 divided by 2n plus 1 factorial. Okay. So with cosine, kind of the same thing. We see it. Of course, the difference there is with cosine, we end up having all of the even power terms, whereas for sine, we have all the odd power terms. Next, we have tangent inverse. And so tangent inverse looks very similar to sine. The only difference is that for sine, we have 2n plus 1 factorial in the denominator, whereas for tangent inverse or arc sine is just 2n plus 1 in the denominator. Also, we know that the radius of convergence is 1, and therefore our interval of convergence ends up being from -1 to 1, where of course the end values -1 and 1 are also included. And of course this makes sense because we know that for tangent inverse, the domain of it is all values in between -1 and 1, including the end values as well. So we also have natural log of 1 plus x. We see that that's just the summation where n is equal to 1 of -1 raised to the n minus 1 times x raised to the n all over n. Our radius of convergence is 1. And for this one, we see that we choose values of x in between -1 and 1. We include +1, but we exclude -1. And of course, that makes sense because if we were to plug in a -1 right here, then that would give us natural log of 0. And of course, we know that the natural log function cannot be evaluated at 0 or a negative number. So makes total sense why this particular power series version of natural log of 1 plus x would not be able to converge when x is equal to -1. So we also have 1 divided by 1 plus x. And notice that this is a little different than the one that we talked here, 1 divided by 1 minus x. Okay. So of course the main difference here is that every other term ends up being negative. Pretty much everything else is the same though. And of course our radius of convergence is 1. And as long as we choose values of x in between -1 and 1, everything is good there. So the very last function I have in this list, this is actually the binomial series version of this particular function. And we say that because it's 1 plus x raised to the k. When we try to express things in binomial series form, this is kind of what we deal with. I'm not going to talk too much about the binomial series in this particular video, but I did at least want to introduce it to you. It is a special type of power series. The difference here is that, of course, our coefficients here are expressed as combinations of k things grouped in at a time. And so that adds a little interesting twist to it. And for that reason, that is why I will be making a separate video just to talk about the binomial series. So now what we are going to do is answer questions 5 and 6 by looking at examples of how we actually use this list of Maclaurin series. So now we will get into answering question number 5 that we stated at the beginning of this video. And following an example, we'll answer how we can use power series representation of a function that exactly equals the function f of x to integrate functions whose antiderivatives are not elementary functions, essentially. Okay. So in example 5 here, we're asked to find simply the most general antiderivative of sine of x divided by x. Okay. Or some of you may know it as the sinc function. Okay. Or a version of the sinc function. So I'll go ahead and write that just in case you're not familiar with that notation either. And so here, notice that we know from our list that sine of x can be represented as the summation of -1 raised to the n times x raised to the 2n plus 1 divided by 2n plus 1 factorial. So with that being said here, if we were to divide sine by x, essentially what we're doing here is we're multiplying sine x times x raised to the -1, which would basically just make us subtract 1 from all these exponents that we see here. Okay, and in doing that, we see how we have this new polynomial. And so if we were to look at the pattern, of course, this pattern would end up being a summation of -1 raised to the n times x raised to the 2n plus 1 divided by x raised to the 2n divided by 2n plus 1 factorial. Okay, so the only thing that really went away here is this plus 1. Everything else pretty much stayed the same. So now that we have sine of x divided by x in essentially a form of a polynomial with an infinite number of terms, we can now just take the antiderivative of that polynomial, and then we will have what our most general antiderivative is in Maclaurin series form. Okay, so we look here. Of course, what I've done to kind of intuitively show what's happening here, we know that anytime we take the most general antiderivative, we need to have an integration constant. And of course, with our first term here, which is 1, if we take the antiderivative of 1, we know that that's x. So if we take the antiderivative of x squared divided by 3 factorial, then that's going to be x cubed divided by 3 times 1 over 3 factorial. Okay, and you can kind of see how the pattern is going to ensue. And essentially what we end up having here is for each term, it's going to look like -1 raised to the n times x raised to the 2n plus 1, all that divided by 2n plus 1 times 2n plus 1 factorial. So in short, we could express the sinc function here, its antiderivative, just as this particular power series. Okay. All right, so let's move on to our next example. So for example number 6, we're going to use the result from the last example, mainly what the most general antiderivative of sine of x divided by x, or what the antiderivative of the sinc function is. We're going to use that to evaluate the definite integral of sine x divided by x from 0 to pi. And we want this particular definite integral, which we know one of the interpretations of it would be area under the curve of this function, to be correct to within 2 decimal places. And so that is to say within an error of 1/1000. Okay, so to sort of visualize what's going on here, the sinc function, sine of x divided by x, I'm going to try to draw this here. The sinc function essentially looks like this. So it kind of does this, and it'll oscillate back and forth like that. And of course, this happens here when y is equal to 1, where we have a hole in the graph. And essentially what it is that we're trying to do, and I may not necessarily be totally accurate here, but I'm just trying to give you a basic idea of what's going on. So if this is 0 here, and let's say, right here is pi, then what we're trying to do is find the area under the curve from right here to right here. Okay, so all this area here I'll do in red, put some of this here below, and of course all this here is essentially the area under the curve that we're trying to find. And of course we know that if we can take the antiderivative of whatever this function is, then all we have to do is just say, hey, whatever the antiderivative is, we'll take it and we'll evaluate it at pi minus evaluate it at 0. So we know here, this is essentially what it is that we are trying to do. And since we already have what the antiderivative of sine of x over x is in Maclaurin series form, we could just use that to be able to accomplish our goal here, okay? So we know that what the most general antiderivative of sine x over x is. We know that it can be expressed as an alternating series, like how we see here. And because of that, we're going to reach back and use the alternating series estimation theorem to estimate the actual value of this definite integral within 2 decimal places. So let's go ahead and get started on that. So we'll go ahead and start off by recalling that the alternating series estimation theorem basically states that we need to be able to show that for our particular power series that we're dealing with in this case, that the b sub n plus 1th term is always smaller than or at most equal to the b sub nth term, where this b sub n is just the absolute value of a sub n. And of course, a sub n is just the sequence that makes up the series. So for this particular problem that I'm talking about, everything that we see inside here is what the a sub n is. And of course, b sub n would just be the absolute value of that, which essentially would just get rid of this alternating series part, okay? So this theorem tells us that if we took the absolute value of the sequence that basically makes up the power series that we're going to use to figure out the area under the curve of the sinc function from 0 to pi, then of course we have to know that all of those terms in the sequence are getting smaller and smaller as n is getting bigger. We also have to be able to show that if we take whatever the expression for the sequence b sub n is, and we take the limit of it, it has to equal 0, okay? So if we satisfy these 2 conditions here, then we know that the error, or the remainder, which we also call the error, if we do the absolute value of it, of our approximation for the actual function sine of x over x by using it in a power series, that error is not going to be more than the b sub n plus 1th term, okay? And so our goal here is to figure out what n has to be so that when we find the b sub n plus 1th term, that value ends up being a value less than 0.001. And basically, we would be accurate with the area under the curve of the sinc function to within 2 decimal places if we can do that, okay? So our goal here is to figure out, well, what is b sub n? And then use the b sub n to be able to figure out how many terms of this Maclaurin series representation of sine, well, of the antiderivative of sine x over x do we need, okay? All right, so let's go through the steps that we need to do that. So if a sub n is going to be the sequence in which our series is being used again, and I know I have it here, but I also want to bring it up here as well. So if we are basically using this power series right here for the antiderivative of sine x divided by x, so the sequence is everything that was inside the summations, and of course b sub n is just going to be everywhere where we see n. We are going to have n plus 1, and of course absolute value of that gets rid of the -1 raised to the n, okay? So we have that. So here, what we are trying to do first is make sure that we show beyond shadow of a doubt that any b sub n plus 1th term is always going to be smaller than or at most equal to the b sub n term, okay? So here for n being greater than 0, one fact that we know here is that if we were to do 2 times n plus 1 times 2 times n plus 1 factorial, and I'm essentially getting that from what we have here as far as how the antiderivative of sine of x over x looks in power series form. So we know that if I was to essentially, for these i's, if I replace them with n plus 1, this quantity would be larger than if I just had n's in place of those i's right there in the denominator. Which also means that if we simplify everything, 2n plus 3 times 2n plus 3 factorial is greater than 2n plus 1 times 2n plus 1 factorial. Okay, so now that we know this, if I was to make fractions out of these, okay, then since I know that 2n plus 3 times 2n plus 3 factorial would have a larger denominator than 2n plus 1 times 2n plus 1 factorial, then when I make this a denominator, I know that the fraction here is going to be smaller than the fraction I will make up here, provided it has the same thing there. So here, notice that that's exactly what I end up doing here. Okay. Now, notice here that I have -1 raised to the n times x raised to the 2n plus 3 to kind of match what I have going on here. And here I have x raised to the 2n plus 1 times -1 raised to the n. And of course, that matches that. Now, I know that 2n, what I have here is essentially x raised to the 2n plus 1 times x squared. So I do know that. And I know that we have an x squared here that is not over here. Now, the reason why this particular fraction here will still be smaller than this one is because even though this is multiplied times an extra x squared, this 2n plus 3 factorial is so much more, it's much larger than this x squared is. So with it contributing to, all right, well, what is going to be the value that we're going to use here? Yeah, this x squared is going to amount to something very small in comparison to what n would be. Okay. So because of that, this denominator is just going to be much, much bigger than what we have here. So that's why this fraction will still end up being smaller on this side than it will be on this side. All right, so if we carry on and we go ahead and take the absolute value of everything that we see here and simplify as much as we can, then we get what's on this very next page here. And I'm just erasing this so that you can see that what I've actually done here to get to this point is just simplify what I had here. And so now that we have that, then we want to allow our a sub n to be -1 raised to the n times x raised to the 2n plus 1 divided by 2n plus 1 times 2n plus 1 factorial. In other words, we're going to allow this to be the a sub n. And thus, we know that a sub n plus 1 is just same thing as this. Everywhere where we see n, we replace it with n plus 1. Now, why is it that we're doing that? Okay. So the reason why we're doing that, because again, we need to be able to identify that b sub n plus 1 is smaller than or equal to b sub n for our values of n larger than 0. Okay. So here we have a sub n, have a sub n plus 1. If we take the absolute value of a sub n and absolute value of a sub n plus 1, we have our b sub n and our b sub n plus 1. And notice here that we essentially have the case that we started off with up here. Okay. So to put this real simple, I kind of figured out what b sub n and what b sub n b sub n plus 1 was supposed to look like. So this is essentially what your b sub n is. This is your b sub n plus 1. But we made the connection now by saying, hey, now that we have these expressions, we can let the a sub n plus 1 be these alternating sequences. And thus, when we strip the alternating series factor part of it away, we now have the b sub n and the b sub n plus 1 that we want. So we know that for our antiderivative of sine of x over x in power series form, the corresponding sequence that goes with it, for every non-negative term that we have that is b sub n, we know that b sub n plus 1 is going to be a term smaller than it, or at best equal to it for all values of n. Okay, so we've actually shown this very first condition here. Okay, so we kind of took a rigorous approach on that. Of course, the second condition is easy. I know what b sub n is. I just take the limit of it as n approaches infinity and hope that it ends up equaling 0. And so that's what we'll show next. So the limit of what our b sub n is, which is, of course, all this stuff. Here, let me get my pen working here. Yep, so all this stuff here. Note that since our limit operator has a variable of n, it's really not going to understand what's going on right here with this x, but we don't really have to worry about that, and I'll show you why. So here we know that we could take the limit of this sequence function and we can break it up as a limit of the product of two sequences, and then using our limit laws, we can just do limit of the first sequence times limit of the second sequence. Okay. Now, we don't have to know what the limit of this is going to end up being. If you note here that this x raised to 2n plus 1 divided by 2n plus 1, this is essentially the absolute value of the sine function. Okay. And really, if we look at this, we know that this limit here, of course, since this function kind of goes back and forth like that, it's really not going to exist. But the thing that's going to control what this limit actually ends up equaling is the fact that this 1 divided by 2n plus 1 is a rational function that is bottom heavy, meaning that the degree of the denominator is larger than the degree of the numerator. So we automatically know that this limit goes to 0. And so what you essentially have is a function. You're trying to study the behavior of a function that's oscillating in between -1 and 1, going back and forth, multiplied times a function that's essentially going to 0. Doesn't matter what's going on here. If we take this and multiply it times a function that's getting smaller and smaller, then the product of those functions is behaving like it's getting closer and closer to the x-axis there. Okay, and so this is why this particular limit here, even though I would have, this sine of absolute value of x here, I left the limit off, but really this would be like a does not exist kind of case. But if we were actually going to evaluate the limit for that, but to keep it real simple, what we can do is just say, well, hey, let's just keep this as limit as n approaches infinity. We see that the other part goes to 0, and doesn't really matter what all this is. We just know it's going to 0 again. Okay. So that's why it ends up actually equaling 0 here, and everything works out fine. So we've met the two conditions. So we see that b sub n plus 1 divided by b sub n, b sub n plus 1 is less than or equal to b sub n. And of course, the limit as n approaches infinity of b sub n equals 0. So we know that what we're dealing with meets those two conditions. So what that tells us is that our error, which is going to be absolute value of r sub n, can be no more than the b sub n plus 1th term. Okay, and that comes from the alternating series estimation theorem. And of course, the b sub n plus 1/th term, we've already found out what that looks like too. Okay. So now that we know that, all we have to do is keep on plugging in values of n into this expression until we get a number that is lower than this 0.001. Okay. And so that's what we're going to do next here after we, of course, go through the whole thing of taking the antiderivative. So at this point, we're going to go ahead and say that, hey, the antiderivative of sine x over x from 0 to pi is just taking this particular power series, well, Maclaurin series, I should say, and evaluating it from 0 to pi. And of course, if I do that, then how I've done this to kind of make it easy, I'm just looking at it for each term. So I know that x would have to be evaluated from pi to 0. The next term, x cubed divided by 3 times 3 factorial, would have to be evaluated from pi to 0, so on and so forth. Okay. So, of course, anytime I plug in 0 in for any of these terms, it's all going to end up being 0. So really, all I'm concerned about is what happens when I plug in pi into my variable x. And so we see that we end up basically having a polynomial that looks like this if we were going to express the first n terms of it. Okay. So in order to find an estimate here, I am going to have to be within 2 decimal places. And I know that whatever my b sub n plus 1 is, it's going to have to be within this amount here. Okay. So what I do is I take this b sub n, which now looks like this, and I plug it in for several values of n. Okay. So we're going to start with n equals 3 here. So just to kind of give us a head start here. So we could have did n equals 1 and n equals 2 if we wanted, even n equals 0 if we wanted, but kind of knew that, hey, we're going to need at least 3 terms here. So we see here at the third term, plug it in, we get 0.086. We plug in 4, we get 0.009. We're almost there. N equals 5. We see that the amount that we get is a number that's smaller than 0.001. Okay. So here we know that we would need to use the first 5 terms of our polynomial equivalent, or our Maclaurin series equivalent of the antiderivative of this particular function here, which would essentially be the first 5 terms of this term. Okay. Now, the other reason why we started off with n equals 3 is because, of course, n equals 1 is here, and that's pi, right? So we know that's far off from 0.001. And also notice here that I'll have odd terms here. So I wanted to start off with an odd value of n just to kind of get me closer quicker, okay? So once we're done here, then essentially we see that we are able to approximate what sine of x divided by x is, well, the antiderivative of that, I should say, from 0 to pi. We're able to write it out in Maclaurin series form here, and we can approximate it with the first 5 terms of this particular series. Now, if we wanted to know what is this exactly, then of course we would have to do what I'm saying here, plugging in the pi for x and have this be infinity. But again, all that we're really concerned about is approximating it to within 2 decimal places. So here I could put, approximation equal to signs there. All right, and so that is how we approach taking the antiderivative and evaluating the definite integral of a function that does not have a natural elementary function antiderivative to it. So we have to look at the power series representation of it and then figure out, well, how many terms I need to look at to have the kind of accuracy I want. So that's in general what we do. Okay, so for the last two examples that we're going to look at, we're going to see how we can actually take the Maclaurin series of e to the x to form the power series for the function 1 minus x times e to the x. So essentially, we're going to see how can we multiply two functions together, one of which will have a power series representation, or in this case, Maclaurin series representation, to be able to get what we need. Okay, so of course, we know that e to the x can be represented as the Maclaurin series of x raised to the n divided by n factorial, summation of that from n equals 0 to infinity. Of course, this is what it looks like whenever we list that out. And so here we also know that 1 minus x is already a polynomial. So we don't need to change that. However, what we do need to do is we need to take this 1 minus x here, and since our summation, its variable, it's n, it looks as this as a constant, just like it looks at x as a constant. So what we want to do is slide that on the inside of the summation operator. Okay. So when we do that, essentially, we can just take this x raised to the n and multiply it times 1 minus x, which gives us x raised to the n minus x raised to the n plus 1 divided by n factorial within our summation. And so from there, we can just go and start plugging in values of n to see what the pattern is going to look like. And of course, once we plug that in here, we see that this is what the pattern ends up looking like for what the function 1 minus x times e to the x would look like as a power series. All right, so in my final example here, instead of looking at a function that is going to be 1 minus x times e to the x, so instead of looking at that, now I'm looking at what happens whenever I take e to the x and I divide it by 1 minus x, okay? So in this case, we see that e to the x divided by 1 minus x is the same as saying e to the x times 1 divided by 1 minus x, okay? And so note here that for our summation rules that we do not have summation operator rules that allow us to multiply two series together to equal just the product of the sequences, and then you just do the summation of that. So we don't have that. So this is not a real rule. So because of that, what we're going to have to do is actually figure out what is the Maclaurin series version of e to the x and of 1 divided by 1 minus x, and then literally multiply those together, which I'll be honest is a pain, but the good thing is that in most of these situations, all that we really care about is having enough terms to approximate to the accuracy that we need it to be. And of course, that helps out a lot because in that case, we're not expected to, list an infinite amount of terms, and we're not also expected to figure out, well, what's the pattern going to be so I can represent this in a nice compact power series form. Okay. So we see here that e raised to the x, its power series equivalent looks like what you're seeing here if you list it out. And for 1 divided by 1 minus x, this is what its power series equivalent looks like whenever you list it out. And of course, I have the actual compact power series versions there. So now from here, all we have to do is just multiply. And so how I'm doing that is I'm literally doing one thing at a time, okay? And it does take a minute to write all this out, but the concept is relatively simple. So here, all I've done is I said, okay, well, I'm going to take 1 and I'm going to multiply it by all these terms first. Then I'm going to take x, which is this x divided by 1 factorial. 1 factorial is just 1. So x divided by 1 is just x. So I'll just take x, and then I'll multiply it times all these terms as well. Then I'll take 1/2 x squared, do the same thing, multiply it times all those terms. And that's what you see me writing here, okay? And so I do it with these first 4 terms I have here. And then, of course, I just list out what the results are whenever I would do that. And if I needed to keep on going, I would do that. And that's what the plus ... represents. So from this point, what I'm doing here is I'm, out of all these terms that I have listed, I am grouping them in terms of what constants do I have, what are the like terms with x in it, what are the like terms with x squared in it, what are the like terms with x cubed in it, what are the like terms with x to the 4th in it, what are the like terms with x to the 5th in it, what are the like terms with x to the 6th in it, okay? So I have all those things listed there, and here, that is what that ends up being, okay? So once I list all that out, add up all these constants for each of the like terms, and I see that this ends up being the result, okay? And of course, this is just for those first 1, 2, 3, 4, 5, 6, 7 terms, okay? If I needed more accuracy, I would have to come back up here, list out more terms here, list out more terms there, and then of course, that would make this part longer here as well. So at the end of the day, you see what that ends up looking like. So therefore, our e to the x divided by 1 minus x actually looks like this particular polynomial here. And of course, we don't know exactly what that would look like in compact power series form. It's not worth it to try to figure it out. So we'll just leave it like that and know that if we need to use it for anything, we may have to list some more terms out depending upon how accurate we want our answers to be. All right, so with that being said, that concludes this particular video. We've answered questions 4, 5, and 6, and it concludes the video series on Taylor series and Maclaurin series and their corresponding polynomials. I hope this video series helped. Take care.